everybody. Today we're going to talk about section 4.7 and a little bit 4.10. This will probably be shorter than most of them, but this is the last distribution we'll cover, and we're going to talk about Chebysheffs as dealing with continuous random variables for a second. So let's get into it. So the last distribution we're going to speak about is called the beta distribution. There are many others we didn't cover in this class, but we can only cover so many because it kind of gets convoluted at a point. But once you understand how distributions work, basically, you can work with about any of them. But the beta distribution is the last one we'll deal with. And it is another two-parameter density function, and it's got alpha and beta as its parameters. Those seem to be consistent Greek letters they use in with a couple of different distributions we've seen. This PDF, however, is going to be defined over the interval from 0 to 1. So usually the values of y are some kind of decimal value. And this is often used to model proportions rather than, just regular numbers we deal with, like we've been dealing with in the gamma distribution. We went from 0 to infinity, so we could have any number in that range. Whereas this one's going to deal with mainly proportions or ratios. So such things as, like you see here, the proportions of impurities in a chemical product, or proportion of time used in that a machine is under repair, the proportion of gas supply sold in a given week, anything that deals with a proportion, essentially, the beta distribution can be used to model over a continuous range. There are some discrete random variables distributions that can also be, let me say that a little clearer. There are some discrete random variable distributions that can also be used to model scenarios like this as well. As a matter of fact, one that we didn't cover is called the Bernoulli. I think it's Bernoulli distribution. I think I'm thinking of that one right. But anyway, it deals with values between 0 and 1, or that are strictly 0 or 1, but it's kind of similar in a way, a little bit different. But you also see some similarities when we take a look at this in a minute that might make you think of the binomial distribution a little bit, and there's good reason for that as well. But let's get into it. So here's the beta probability distribution function, the PDF function. All right, little f of y here is equal to y to the alpha minus 1 times y1 minus y to the beta minus 1. And this kind of looks, this part here looks very similar to like our p times 1 minus p in the binomial distribution, so it kind of has a similar feel to that. All right, and then that's all divided by b of alpha comma beta, which is what we call the beta function, which is down here. All right, and that exists from 0 to 1. And the beta function is a kind of a multi-build of like it's the gamma distribution with several different versions of the parameter thrown into it, as you see right here. So that integral from 0 to 1 of y to the alpha minus 1 times 1 minus y to the beta minus 1 dy over 0 to 1 is what we call the beta function, and it's just gamma of alpha times gamma of beta over gamma of alpha plus beta. So that's how the book gives this definition. When you think about the beta probability distribution, we're not going to worry too much about this guy here. I'm not going to have you really do anything with him. We're not going to worry about that. We're going to deal with giving you alpha and beta values that are usually whole numbers if we ask you to do integrations. So you can just jump right to this. But your beta PDF should really look like the following. Little f of y should be gamma of alpha plus beta divided by gamma of alpha times gamma beta, all times y to the alpha minus 1 minus y to the alpha minus 1. So this is really here what you should use if you're asked to do an integral, because we can deal with those nice whole numbers thrown in for alpha and beta. It's easier to deal with, and since there's also no calculator function that deals with this, and we're not going to be able to write any little nifty programs on your calculator, we'll deal with this PDF right here. Okay. So you have to be given everything in there to be able to utilize this. All right. Very similar to the gamma distribution function, the beta distribution function has its alpha is its shape parameter. The alpha really adjusts the shape of the parameter of the distribution curve, and beta, the scale parameter, still called the scale parameter here, really fluctuates how the scale of it is. If you look here real quick at the curve that represents alpha equals 2, beta equals 2, it's really looking at this curve right here. And when alpha and beta are equal in this particular circumstance, this kind of looks a little like a normal bell-shaped curve without the tails going off on the sides of it. This doesn't really mimic anything other than that. And notice that it begins and ends right at 0 to 1. When alpha equals 3, beta equals 3, we see that as long as the alpha and beta are equivalent to each other, they kind of have this nice symmetry to the curve. If you notice the trend here, it's like the center's right here, right about here, about halfway through, about 0.5, and that's the same thing for the alpha equals 2, beta equals 2. But when you change the values of their alternating values or their different values for alpha and beta, such as the last option here, for alpha equals 5, beta equals 3, then the apex of that curve, or the top of that curve, is kind of shifted. So when alpha got bigger, it shifted the curve to kind of make it more what we call a negative skewed distribution, where it actually starts to have a tail here on the far end. All right, and then it has a lot of its data towards the one side, so a lot of the probabilities of this are going to be above 0.5. If your alpha was smaller and your beta was bigger, it tends to kind of pull back the opposite direction. So it would almost be like, let's see if I can find a color that will show up on here good. It would almost be, instead of like that one, it would be almost like this. So it'd kind of be the opposite of that. All right. Anyway, enough about the look of the distribution, although it's important. Let's actually, the expected value and variance of this distribution are made up of alpha and betas, a little more complicated than the gamma distribution, well, a lot more complicated looking than the gamma distribution one was. And when you have to find these things using moment generating functions, it's a lot of fun. I can tell you that from experience, because they made us do that in grad school. I'm not going to make you guys do that. But there's the formulas. You guys can plug into things. So if you're asked for the mean and the variance of the beta distribution, these are the formulas you want to use. All right. And so let's just do an example real quick of utilizing the beta PDF function that we saw. And that'll be pretty much it for the beta distribution. You guys kind of know how to deal with these things by now, I would say. So I'm going to go over here and look at the question. So example 1 says a gasoline wholesale distributor has bulk storage tanks that hold fixed supplies and are filled every Monday. Of interest to the wholesaler is the proportion of this supply that is sold during the week. Over many weeks of observation, the distributor found that this proportion could be modeled by a beta distribution with alpha equal to 4 and beta equal to 2. Find the probability that the wholesaler will sell at least 90% of her stock in a given week. So they're really asking us to find the probability that y is greater than or equal to 0.9. All right. Well, that requires us to use the integral, and we're going to go from 0.9. Remember, this distribution stops at 1, so we can't go any higher than 1, so it's from 0.9 to 1. And that's going to be of gamma of alpha plus beta. So it's gamma of 6 plus 4 plus, I'm getting ahead of myself, of 4 plus 2, all over gamma of alpha times gamma of beta times y raised to the alpha, which is 4, minus 1 power, times 1 minus y, to the beta minus 1 power, which is 2 minus 1 dy. So that's what we have to deal with. So over here to the side, I'm going to just figure out real quick what gamma of 4 plus 2 over gamma of 4 times gamma of 2 is equal to. And that gives me gamma of 6 over gamma of 4 times gamma of 2. And remember, the gamma function is always the number inside minus 1 factorial. So this is really equal to 6 minus 1 factorial over 4 minus 1 factorial times 2 minus 1 factorial, which just gives us 5 factorial over 3 factorial times 1 factorial, which should give me 120 divided by 6, which should give me about 20. So that whole complicated looking thing up front just devolves to 20. And we're really now looking at the integral from 0.9 to 1 of 20 y to the 4 minus 1 gives me to the third power, so y cubed, times 1 minus y to the 2 minus 1, which is the first power, so it's just all that right there. And that made our integral much simpler looking. So it looks scary at first, but it gets kind of nice looking at the end. And actually this is still better than the gamma distribution, just as a side note, because we don't have to use integration by parts. Oftentimes with this 1 minus y, you'll be able to expand it if you had to. It might not be a fun expansion, but you could expand it if you had to. And then multiply everything together. So I'm going to distribute that 20y cubed into the parentheses so that we're really just integrating 0.9 to 1, 20y cubed minus 20y to the fourth dy. And that makes that a little bit simpler. So the integral of 20y cubed should be 5y to the fourth minus the integral of 20y to the fourth should be 4y to the fifth. Double check myself over here. 4 times 5 is 20. Take away 1 from 4, it'd be 3. 5 times 4 is 20. Take away 1 from 5, we get 4. So that's still good. From 0.9 to 1. So we're looking at 5 minus 4 when we've been plugged 1 in for y to the fourth and y to the fifth. Minus, now putting in 0.9, we get 5 times 0.9 to the fourth minus 4 times 0.9 to the fifth, which equals, it's going to end up equaling 1 minus, let's see what that comes out to be, 0.91854, and that comes out to be roughly 0.0815. Okay. So integrating the PDF on this one's the easier way to go, because the CDF for the beta distribution is not an easy thing to deal with, and it's harder to program in something. So that's why you don't see it in calculator packages very often. All right, that's pretty much it for the beta. Let's talk about Chebysheffs a little bit. So everything we've learned about the empirical rule thus far in Chebysheff's theorem applies to continuous random variables in the same way it did to the discrete random variables. So we learned about Chebysheff's theorem back when we were dealing with discrete, but these two formulas we learned back then still apply to the Chebysheff's theorem. So it's really not different from that, other than your mean and your variance in a lot of cases. With the continuous are just different formulas, right? So depending on what you're dealing with, you may have to come up with a mean and variance based on that particular distribution to be able to utilize these formulas. It's still all about finding the k value so that you can find the probability of observing being so many distributions away from the mean. Recall this one here finds the area between two values that are k standard deviations above and below the mean, right? This is negative k, this represents negative k sigma and positive k times sigma away from the mean. And this one right here finds the area of the curve outside of those two. I think we discussed that a little bit back then in the Chebysheff's inequality back in 3.11 or 10 or whatever it was. So instead of finding, this finds the area between, this one down here finds the area out. Do that. This one finds the area out here. All right. So let's do an example using this real quick, and this lecture will be pretty much done. All right, so example 2 says, suppose that experience has shown that the length of time y in minutes required to conduct a periodic maintenance check on a dictating machine follows a gamma distribution with alpha equal to 3.1 and beta equal to 2. A new maintenance worker takes 22.5 minutes, so it takes 22.5 minutes for this new worker to check the machine. Does this length of time to perform a maintenance disagree with prior experience? So prior experience, we have our alpha equal to 3.1 and beta equal to 2. So that prior experience and the fact that we're dealing with the gamma distribution are all important features here. All right. We need to figure out what from prior maintenance experience and the distribution that was built using this gamma distribution, what the mean and the variance are for that. So there's some information we need that comes strictly from the gamma distribution, right? And with alpha equal to 3.1 and beta equal to 2. So we need to know that the mean, which is the expected value of y, if we recall from that previous lecture, on gamma, that's just alpha times beta. So that's just 3.1 times 2, which means that the mean for the number of minutes required to conduct this maintenance check in prior experience was 6.2 minutes. All right, so that's an important piece of information. The variance for this guy, remember, is alpha times the beta term squared. So that's just 3.1 times 2 squared, which gives us roughly about 12.4 minutes squared. But notice that in the Chebysheff's inequalities here, that the sigma is just the standard deviation and not the variance. So we need to go ahead and calculate the variance as well, or the standard deviation as well. So sigma is just the square root of 12.4, which gives us roughly the standard deviation of 3.52 minutes, all right, give or take. All right, so that's what we need to discern from that gamma distribution function. So it still doesn't answer the question, does this length of time to perform maintenance disagree with prior experience? So how do we go about answering that question? Well, if this new time that this new worker has gotten is so outside of being normal, right? In other words, if that time exceeds the previous mean, which it does, by a large enough margin that we should not see that happen, like the probability of seeing that happen is so unusual enough, then we'd say, yes, this disagrees with the prior experience. So that's what we can use Chebysheff's to help us do, all right? So we make a note here. Note that 22.5, which is our y value in this case, exceeds the mean mu of 6.2 minutes. Right? So that's kind of important. So we need to use, out of the two formulas we saw, we want to see, we want to think about this as that one with the outer tails that I mentioned in the previous slide. So we want to know what the probability of something falling that out around 22.5 or further. Let's see how unusual that is. So we need to use the probability that absolute value of y minus mu is greater than or equal to k sigma, because this is we're exceeding, k sigma is exceeding the mean, and that's going to be that's always going to be less than or equal to 1 over k squared. All right. So what we really need to do is use what we have at our disposal in this formula to find the value of k, and then determine the probability based off the value of k to see how unusual it is. And that'll tell us whether or not the length of time this new guy did the job in disagrees with prior knowledge that we have based on the distribution. So if it's unusual, then we can probably conclude this guy's slow. Let's see what happens. I'm going to add another page here because I'm running out of room. And let's do the rest of this on another page. So write down this again. So we know the y value we have is 22.5. That's the value the guy did the job in, or did the maintenance in. We know our mean is 6.2, and we know sigma was equal to 3.52. All right. And what else do we need? We're using this formula right here. So the first thing I need to do before I finish up with this guy, or utilize this guy, is figure out what k is, because k is really the thing that we're missing. So over here to the side, I'm just going to take y minus mu. This should be greater than or equal to k sigma, and I'm going to play with that to find k. So we know our y is 22.5. We know our mean is 6.2. We know this is to be greater or equal to k times sigma, and sigma is 3.52 times sigma. So now I'm just really, not sigma, 3.52k. So I'm really solving this thing for k. So 22.5 minus 6.2, we divide both sides by 3.52, we should know what k is. And when we do that, we get that k, it's going to be roughly about 4.63, so we're just going to assume k equals 4.63. That's the biggest value it can be. It has to be, k is always going to be less than or equal to this value in this case, but we're going to assume the greatest value, so k equals 4.63. So going back up here, probably that some y value minus 6.2. So I'm not plugging in the y value there intentionally, because the y could be any value in this case, because we're not really worried about what y is any longer. But k sigma we're concerned about. K specifically is 4.63. That's really the thing we're worried about. 4.63 times sigma should be less than or equal to 1 over, I'm making a mistake here, k squared. I don't know why I wrote sigma over here, folks. K squared is 4.63 squared. So that has to be less than or equal to, when you do that in your calculator, you should get 0.0466. So that's below the 5% threshold that we consider. Anything smaller than 0.05 is considered unusual. So what we can conclude here is the following. With such a low probability of occurrence, we should conclude that the new maintenance worker is slower than the preceding workers, is slower than the preceding workers. And remember, this is based on our assumption that the distribution of maintenance times has not changed. Okay. We could have assumed, if we hadn't assumed that the maintenance times haven't changed, then our other option of assumption here would be that maybe the maintenance times have changed and we need to regroup and maybe collect more data and see if it still fits the same alpha and beta that we had before, because maybe the mean has changed somehow. That would require us to do a whole lot more work. And so you're, in this case, it's probably better off assuming that the distribution of maintenance times over all workers that you have doing this kind of job on all of these machines is the same as it always has been. But if you're questioning that, then in reality you'd want to go back and collect more data to see what your other maintenance workers might be doing. Unless you just have the one guy, then you just have to assume that he's slower than your last guy or a girl or whoever it is doing the maintenance work was. So that's pretty much it to that. I'm probably not going to ask you to use Tchebysheffs very often. Actually, I don't think I'm going to ask you to do it much here down the stretch. What we did in this discrete chapter was good enough, but it's worth knowing that you can do it here as well, and that this comes up and is useful in different places. So anyway, that is it, gang. There are a couple of homeworks. There's really no homework in 4.7 because a lot of the homework questions in 4.7 on the beta distribution are ones that you need to use applets for. And since we're not really using applets in this class, try our example 1 that we did with different values of beta, alpha and beta thrown in the mix to see how your probabilities change based off of that. See how changing alpha and beta around can change your probability outcome for the most part, and you get some changes will make them smaller, some will make them bigger. So it's worthwhile just to see if that's a good way to practice that one, and just to see what happens. Because in math, a lot of times that's what we do. We experiment. We don't just have somebody giving us the answers. So sometimes we have to experiment to see how things play out. That's a good way to do that there. And then in 410, you can give problem 147 a shot, I think. Let's see. Problem 147. Oop. Blow this up. It's a cereal box filling thing. Yeah. The manufacturer wants the actual ounces dispensed Y to be within 1 ounce of mu at least 75% of the time. Hint, hint. When K equals 70, when you're talking about 75%, K usually equals 2 in Tchebysheff's theorem. What is the largest value of sigma, the standard deviation of Y, that can be tolerated if the manufacturer's objectives are to be met? Play with it a little bit. It might not be exactly 2 in this case, if they're wanting to be within 1 ounce of the mean. All right, but that's one you can play around with. And 146 is probably also a good one because it's giving you the mean and standard deviation right off the bat and asking you what interval you would suggest. That's another good one to practice as well, even though I didn't put it on the slide itself. And if you want the answer to that one, I will gladly give it to you if you practice it. All right, and that goes for any of the rest of these as well. So there's not that much in that section, which is why I'm not spending a whole lot of time on it. All right, gang. Thanks for a great semester. This is the last lecture I've recorded, and bearing with me. And if you have any questions, once again, reach out to me. Won't be too much longer before I'll be releasing the final exam to you. So good luck to everybody, and take care.